say, hey, if this is a great webinar, if you're just learning how to work with the Celigo, the Analyze tab can be a little bit daunting because it's image analysis parameters. And so that's why we're holding this special webinar for this topic. It's something that'll help understand the details of how your image is actually being analyzed. So hopefully at the end of this, you'll have a little bit more clarity and understanding of how to set up the parameters in the Analyze tab. So on the Celigo, you basically can reanalyze your images any number of ways or times. So it doesn't matter if you make a mistake this time, you can always redo it. Okay, so here in the Analyze tab, the parameters look like this. And we're going to basically cover the sections that are on the Analyze parameter. So the top portion is the general well mask area of the parameter column. The next section is the object identification, where the outline is going to pick up your objects in the images. And then the third portion we'll talk about is the pre-filtering section of the objects that you define in the identification section. How can you filter out the things you don't want? And that's generally how I operate when I set up the parameters. I work from the top and work my way down. And so you can see how I set it up with 1, 2, 3. So it's an easy way to remember. Okay, so to cover the content of the well mask, I want to describe to you some of the different well types that you're going to run into. For large wells, like 24 here and 6 wells, these are manufactured not for imaging but for growing, and they're really not meant for imaging, but we've learned how to work with them on the imager, and we've learned how to set up some algorithms that are defining the well mask area. So here is a colony application for the colony formation assay. We're identifying these cells that have grown into colonies. It's doing a good job identifying them, but you can see that outside the well wall, we have picked up the objects in the well wall itself. So what we've done is we've created this graphic overlay called the well mask that will actually draw a line on the image and anything on the inside of the line. So if we turn on the well mask with this little checkbox, the well mask graphic overlay will show up on the image as an orange line. So now this is actually going to draw a line according to the plate specifications that you defined when you first set your scan up. You pick the plate type and the manufacturer. So those dimensions are recorded in the profile. So the original is coming from the manufacturer's specifications, but we've learned that they're not always perfect because it's plastic. So we've created an algorithm called Automatic that uses those dimensions and the image itself to make a better fit of the well wall or the well mask on the well wall. So you can see how the Automatic does much better job than the original. But we still have a few artifacts on the edge of the well. So what we'll do here is just shrink the well mask a little bit so it moves inside, just on the inside of the well wall. So just turning it into 99%, you can see how it eliminates those objects that were being picked up incorrectly. And then the objects inside the well are actually still properly detected and identified. So that's how the well mask works. It's basically eliminating objects outside the well mask and only counting objects on the inside of the well mask. The large wells are what we just talked about. Now I want to talk about a small well. This is a 384 well high volume plate. They typically have square wells but with rounded corners or rounded edges. So this can be challenging for us to draw a well mask. So the definition in the plate profile is actually a square. So we had to get clever in the automatic well mask. Oh, well, first, let me just tell you what's in the image. We have Drex 7 stained cells, so that's a dead stain in the far red channel. And the problem with this dye is actually it has a lot of background, and that will actually be difficult to, on the edge of the wells, it's picking up the objects. The dead cells are picked up properly, but you can see where I have the background from the dye next to the edge of the black wall. It's actually picking up those as objects, which is not correct. So we'll use the well mask to help eliminate those incorrectly detected objects. So the automatic algorithm for the well mask actually merges a square with a circle to create these rounded corners. So this helps better define a well mask for this unusual plate shape. So the original here, if you turn it on to original, you can see it's a square, and that's just the plate definition from the manufacturer. So we typically will use the automatic well mask mode for this plate type. Now it's not perfect just yet at 100%, we're still getting a few objects. So what we'll do here is just shrink the well mask so it sits right inside the well wall. And that's, you can see as we shrink it, it starts to eliminate those objects. And we are clipping a little bit of the well, but considering how many objects were being picked up, it's really minuscule considering the objects that were incorrectly detected. So typically for this plate type, I'll do a 95% shrinking of the well mask, or set it at 95%. And just to verify, you can navigate around on the plate to see other wells and see how is it performing. And it's properly identifying the DRAX 7 dead cell stain in the far red. It's doing a good job, and there's only a few of the cells outside the well mask that are not being detected, but I'm okay with that. As long as every well is being treated the same, it should be fine. So it's doing a good job. So you've seen basically the large well format and now a small well format. Now here's a 96 well plate. It's a black wall, clear bottom, film bottom plate. It also has its imperfections. Sometimes the well mask or the well shapes are slightly off, typically more on the edge of the wells or the plates. So here you can see when I turn the well mask, it's just outside the well wall. And when you turn on the graphic overlay, the algorithm for detecting objects will get confused with this black wall and bright field background and start to detect those as objects. So what we can do is, actually, let's just look at the original profile that comes from the manufacturers, and you can see where does that sit. Okay, so it's inside the well. So let's do the automatic and then shrink it just a little bit. So again, the automatic uses the specifications and the image to better define where the well mask should be located. All right, so large object applications have unique viewing features and analysis features. This is also located in the general section. Let's cover the viewing feature. So we have some terminology to learn. FOV stands for field of view, which is actually one camera image. And then field of regard is when you take 16 images together, that's how far the galvos can go, and then it stitches them together, and that's this view that we're looking at currently. And then the third view is the whole well view. Typically large applications, you're going to want to use the whole well or field of regard FOR view. This makes the analysis parameters much easier to set up, and I highly recommend using the whole well view for that. So today we'll just use the FOR version. Okay, the next section is to talk about the analysis resolution. So typically the pictures are taken at 1 micron per pixel, but we can analyze the images with less resolution, meaning for this instance, a 2 micron per pixel is actually merging a 2 by 2 pixels into 1 so that it has less values or information for it to analyze the image. This is good to have for large applications like confluence, the colony suite, or spheroids, because you don't need to have that high detail from the 1 micron per pixel image when these large objects are being identified. You really just want to count the colonies and get the general size of the colonies. You don't need to have the actual cell by cell outlining. So changing the resolution to a higher value creates less resolution on the analysis, and it makes it much faster for the system to analyze these large well images. So like a 6th well will just be amazingly fast if you increase that value, say up to 3 or 4 micron per pixel. So currently looking at a 24 well plate, and as we increase that value, it lowers the resolution of the analysis only. it's going to resize the image according to that resolution, but the picture image is still saved in your computer at a 1 micron per pixel resolution. It's just purely how do we analyze it with less resolution. And you can see as we increase that value, how the outline on the graphic overlay becomes a little bit smoother and not as highly detailed around the cells. So typically I will set this general section up first before I move into the next section down below, because you can see how it can adjust or change the graphic overlay significantly. All right, so we just covered the general section with the well mask area. Now I want to cover the object identification. So what's important to note is how the camera is taking the pictures. It's where the pixels are actually having values, where 0 is equal to black and white is equal to 255. And then the algorithm deciphers what is an object according to the pixel object intensity threshold. So how does that work? So in the bright field algorithm, it looks for objects with a bright center and dark edges. So let's see, here's an example of an adherence cell on the Celigo. If you actually drew a line over the center of the cell and then plotted the pixels on that line according to that image, it would look something like this graph here, where you have the pixels on the y-axis from 0 to 255. You can see the white portion of the cell is the highest portion of the image. And so the system is going to ask you to set the intensity threshold, which is this red dotted line. And that value, now anything above that value will be outlined with a green line and a white dot, or a dot in the center. This is what it will call an object. So anything above the intensity threshold is now identified as an object. So that's the bright field algorithm. The fluorescent algorithm is looking for bright pixels over a very dark background. How does that work in practice? So here is an example of a fluorescent cell. Here we have a green fluorescent cell, and if we do the same thing where we draw a line over this cell and plot the pixels according to its value, it would look like this profile. And then when you have the intensity threshold set, which is this red line, and then the system will draw a green or purple outline around the objects above that intensity threshold, it will look like this with a dot in the center. Okay, there's two more algorithms that we're going to cover. So the dark object algorithm is looking for dark objects with no bright centers, just all dark. I rarely ever use this because it struggles with debris in the plate, but you can see in general how the profile looks for a dark cell, and then when you set the algorithm, the objects will outline it this way. It's very challenging when you have a lot of scratches or debris, so that tends to be my least favorite algorithm. The last algorithm was probably one of my favorite ones, the texture algorithm, which we'll cover a little bit more in practice in the rest of this webinar. It's actually looking for texture differences between objects compared to the background, which is very flat. So here's an example of a group of cells that grew into a colony. And when you draw a line over this object, you can see how there's a ton of pixel changes in a localized area. And so that's where you have an intensity threshold set according to texture. And then the green graphic overlay will be outlining the colony of cells rather than the individual cells. So that's how that texture algorithm works. Okay, so let's see how this works in practice. Here we have an example of adherent cells using the bright field algorithm. This is the first one that we just talked about. And the intensity threshold, or that red dotted line, the default here is set up at 15. So it's going to be looking for the bright cells, and that's why you can only see a few of the cells being detected. If you turn off the graphic overlay, you can see how those visually are much brighter than the rest of the cells in that colony. So you can see those bright ones are properly detected, but we're missing the dimmer, more flat cells. So if we lower this intensity threshold from 15 down to 10, and then click make sure you have the auto analyze checked down below at the bottom of the screen. That will update automatically the graphic overlay every time you make a change in the parameters. So just lowering this intensity threshold, you can see how many more cells we're picking up that are flatter and much dimmer, closer to that bright field background. And then we're going to go all the way down so you can see when it's gone too far and you need to move back up. So when we're getting down to the lower values, you start to pick up small little debris that are not cells, but more of like artifacts in the plate and scratches potentially. And that's not what you want. So going too low, you end up picking up way too many things that are not really cells. So let's raise it up a little bit better than that. So for adherent cells, I would probably use on average around the 5 value for intensity threshold. In a minute, I'll show you the suspension cell line. I would probably use a higher value like 15, as you saw in the beginning. So for adherent cells, I typically am around 5 to 3, depending on how flat the cells are. MCF7s are one of the flattest cell types. SKBR3s are also very flat. Those are challenging too. The other parameter you can use in the bright field algorithm is the cell diameter. It's asking what is the average expected diameter of the objects you're looking for. So you want to kind of average what you would expect the diameter of these cells are, probably between 10 and 15 microns. Remember, we're looking at 1 micron per pixel images here. So we can just adjust these values and you can see how the objects you're picking up are actually expanding and getting to be a little bit bigger, or it might merge some cells that are close together. So having, oh, and then background correction is basically when you have wells that have evaporated, the dark edges start to appear because this is how little light, it changes according to the volume. So if you have dark edges, you're going to want to have background correction on, and what it does is it levels the gray values across the well so it's even and it can pick up the cells better. So on average for a 96 well plate, 175, 150 to 200 micron liquid volume microliters is sufficient to eliminate these well edge, dark edges. And then separate touching objects. I'll use this when I have cells that are really grown tightly together. You can see how when I have it off, these cells that are touching each other get merged as one, and then when you turn it on, it will separate them. But if you have sparse long cells, that tends to chop the long cells into two, so it's a challenge. You kind of have to look at your cell type and determine, is it better to have it on or better to have it off? But when it's really compact, I typically will have that on to separate the cells when they're close together. So those are probably the 4 parameters that I'll use for the bright field algorithm: intensity threshold, cell diameter, and then the background correction and separate touching objects. So this is probably a typical setting that I'll have for my adherent cells. So now the section down below is the pre-filtering. It's asking, of the objects you've picked up with the green graphic overlay, how do you want to filter out? So this is a requirement. So here the first thing we see is the cell area. It's currently set as a minimum of 10 micron per pixel squared. If we increase that, you can see how small objects are eliminated. So it's requiring the cells be of a certain size for it to be outlined. It's removing anything smaller. So on average, I would say for adherent cells, I'll probably set that minimum area to be around, depending on your cell type, between 30 and 60. I know it might seem large, but it's really not. As you see, moving it up just a little bit removes a few items. So again, just see what goes on with your cells when you move it up a little bit. I'll go as high as 60 on average, and sometimes with larger cells, I'll even go up to 100. I rarely set the maximum for that one. I never usually have that issue, but if you have large debris that's showing up, you can always use that as a filtering out. So by decreasing the maximum, you can eliminate large debris. So that's doing pretty good. I'm happy with this setting. So honestly, you could probably screenshot this right now. That's probably what I'll use most times for adherent cells in bright field counting. Let let's see. There's one more thing. Let's talk about the cell intensity range and the aspect ratio. I'll cover those, but the cell intensity range I don't use very often, but if you can tell, it's pixel intensity based. So the camera range is from 0 to 255, from black to white, and right now it's capturing every pixel according to all those intensities. But if you have, say, really bright objects that are not cells, you can filter them out, but obviously, or if you have really dark debris, you can filter out by increasing the 0 to whatever it is. How do you figure it out? You just hover your mouse over the object that you want to eliminate and figure out that pixel intensity, which is displayed here at that bottom screen value. It tells you what the pixel intensity is, and that'll help you set the value. So here we have some really bright cells, and they're close to like 120 something. So as we decrease this range maximum down to that value that we just hovered over on top of those bright cells, you can see how they can be removed or eliminated as objects. Not quite there. Keep going. Okay, so there, 128, and you saw the very brightest cells in that colony were eliminated. So it's more about showing you how this works, in that you can remove or filter out objects that you don't want according to their pixel intensity. I very rarely use the cell intensity range to filter things out. I'll use the cell area or aspect ratio instead. Okay, what is aspect ratio? Well, it's length versus width. So if a circle is perfect, it has a value of 1. Adherent cells have a value that is less than 1. So here it's just you type in a value that you want to eliminate, anything that has an aspect ratio less than. So currently it's set at 0, so every object is available to be identified. But if we increase this aspect ratio filter, it basically will start to remove very, very long objects. So let's start with 0.1, and you can see how, okay, there was nothing removed with 0.1. 0.2, you can see very long adherent cells were removed. So I would say this is probably 2 cells that are beginning to divide or had just divided. So I just visually looks like that to me. And then changing it to 0.175 means we can keep that long cell, but maybe eliminate some of these irregular shaped clumped up cells. If I'm using suspension cells, I probably would use aspect ratio more times than not. For adherent cells, I don't use it that often. But if you are looking for cytotoxic effects from treatments, you could probably just count the rounded up cells by pre-filtering out normal healthy adherent cells and just counting the rounded up. They're not quite dead, but they seem to be rounded up unhappy cells. So this would be an easy way for you to analyze your cells, picking up just those rounded cells. All right, so this is an example of suspension cells. And here you have the option to use the bright field algorithm, which we just described, or the fluorescent algorithm, which is kind of a cheat, if you want to say. We found it works sometimes when you're struggling with the bright field algorithm. So I just want to show you an example of how you can use it. So here we have the bright field algorithm selected, and the graphic overlay is picking up those cells, but it's also picking up interstitial areas between the cells because the intensity threshold is set down pretty far low, like an adherent cell line would be set. So that doesn't work too well for suspension cell lines. So you want to increase the intensity threshold for these suspension cell lines. So 10 is still picking up too much content. 15, still too much content. 20, we're getting better, but I probably would go up to 25, and you can see how the very bright center of the cells are being picked up and counted. And so that looks really good. So I like for suspension cell lines, you can probably go between 20 and 30. So So 40 might be, okay, no, 4. 4 is way too low. That's more for adherent cell lines. The other parameter that we were talking about is the cell diameter. So if you think about it, suspension cells are actually smaller than adherent cells, so you want to decrease this diameter to be smaller. And you can see how, even with the lower intensity threshold, we can eliminate those objects in between the cells by shrinking the diameter, because those are larger than 6 microns at this current value. So this is how the bright field algorithm lets you work with 2 parameters, the intensity of the objects in the image, as well as the size of the object that you're looking for. So you can see how, just playing around, that the intensity threshold made much bigger changes than the cell diameter for our suspension cells. So that's usually what I'll work with first, and then the cell diameter, you can kind of guesstimate how big your cells are. If you know your suspension cells, you're probably around 6. If you're adherent cells, you're going to be between 10 and 15. So this looks pretty good for these suspension cells. You can see how the intensity threshold made a bigger difference in the detection versus the diameter. So we've covered a lot on this bright field. What I want to try now is show you how the fluorescent algorithm, which you know functionally how it works, but how can you use it on a bright field image? It's just more of understanding how the algorithm works. Because the fluorescent algorithm is looking for very, very bright objects. As you remember the profile of that fluorescent cell, we can use that for these bright, bright suspension cells. So if you just set the algorithm to fluorescence and then increase the intensity threshold, you can see how, let's bump it from 4 up to, say, 10 maybe. And it does a pretty good job. So now you've got the fluorescent algorithm working just fine for the suspension cells, because they have that really bright white center, which would be what it would find in fluorescent images, the whitest, or the 255 pixel intensity. So here for suspension cells, you can either use the fluorescent or the bright field algorithm. It depends on your cell type, and you'll have to just play around, but you have options. And if you wanted to record these values to try it out right off the bat to your cell lines, you can do that, because we've kind of, I would say typically this is what my suspension cells will always look like, and then the adherent cells you saw, those usually are what I'm seeing as well. All right, so let's show how the fluorescent algorithm works on nuclear stains. So here I have Hooke stain cells. It comes in the blue channel, but just to note that the camera is actually taking black and white images, and the software pseudo colors it for your display. So Hooke's is blue, so it's taking and showing the color as blue. But we can change it to white just for purposes of this teaching webinar. It's a lot easier to see on the screen than blue. So these have these are cells stained with Hooke's, and some of them are really bright and some of them are really dim. But when you turn on the graphic overlay for fluorescence, remember it's looking for pixel intensities that show above an intensity threshold value against a very black background, almost 0. So it's doing a pretty good job. It's typically when you use the algorithm for fluorescence, the intensity threshold is set at 4 and the diameter is set at 10. These are default settings, and it usually does a pretty good job for the nuclei. If you want to find out how big your diameter are, you can hover your mouse over an object and it tells you the X and Y position of where your mouse is located. And so you can tell this is a 1 micron per pixel move. So those are micron values that you can assume. And figure out how big should you set this diameter just by hovering your mouse over an object and measuring the size according to that pixel change. As you increase this diameter, some of the nuclei that are close together will merge together. And that might happen with cells that have just divided, or if you have objects that are super crowded, as you see here. So what we can do is actually use the separate touching objects to break up those cells or nuclei that are very close together. And it will cut them and separate them. All right. Now, it did a good job, but there are a few places where it might have chopped a nuclei in half when it should have. So you have to kind of balance how many times does it do that. Is it so few that you really need to worry about it? Or is it a ton of times that it should not have done it? So that's where you have to look at your images and see what's the better setting to do. All right, so the pre-filtering, again, I'll use that to eliminate things that are not cells but are being picked up, so according to their size. So we're limiting it to, currently, if you set it to 30, you can see that little debris thing is now eliminated. And typically when I'm using hooks, I'm usually using the gating tab. I want to do some other type of subpopulation stuff. So you can use the gating tab to filter out these small objects instead of pre-filtering sections. That's another option. If you'd rather see it in the gating tab and filter out there, you can do it that way as well. Okay, so we've got our well mask. Now I want to talk about the texture algorithm. We've gone through bright field, fluorescence. The texture algorithm is usually found in the Confluence application and the Colony suite of applications. And the default settings are pretty good to start with. The intensity threshold value is really the only thing that you need to set up. The diameter does not work with the texture algorithm, only that diameter works with the bright field algorithm, not texture. The precision is defaultly set at low. Basically, it's how much detail do you want the algorithm to look at around your colony. So typically I'll keep it at low because you don't need all that extra detail to define the colony edges. It's more about getting the counting of the colony and the average size. Having that extra granularity around your colony isn't necessary, and it just takes longer to analyze. So I defaultly keep that at low. You can see how much detail it picks up around the colony, and it just requires too much computer processing power, so I don't really need it, so I'll keep that at low. And you can see how the default setting has done a pretty good job. And the same concept, the higher value you have in the intensity threshold, you'll pick up more textured colonies. If you have very flat colonies, you're going to want to lower that value. Okay, so let's review what we've covered. So here on the analysis parameters, you have the general section, which is usually what I'll work on first, setting your well mask, getting the right size set, and then I'll cover the object identification section, picking up the objects I want, and then filtering out the objects I don't want last. So that's the order of operations that I typically will use for identifying objects in my images in the Analyze tab. I know it was a lot, but if you guys have additional questions, I would like to open up the forum for any additional questions, and you can always email us too. So let's see, what else can I add? I think that's it. Amy, if you want to open up the forum for any questions, that'd be great.
Great. Sarah, I think that was a really wonderful presentation. So like Sarah said, we are opening this time up for any questions. So feel free to type them into the questions bar, and we will receive them on our end, and then I will read them over to Sarah for a Q&A session. And while we're waiting for you guys to type those in, I'd just like to remind all of our attendees that if there's any future topics on the Celigo that you'd be interested in learning about, we'd be happy to hear any of your topic suggestions for future webinars. You can write it into the questions bar right now. You can send us an email at support@nexcelom.com. There's also a short survey you can take at the end of this webinar, and you can type in your suggestions there. We'd be happy to review them for future webinars as well. So I'll give you guys just another minute or so to see if we get any questions that come through for Sarah.
Oh, and Amy, don't forget, well, to my audience, just tell your friends about these webinars. If you just learned how to use the Celigo, these are good refreshers. If you have new people coming into your lab, let them know about these webinars. They've gotten a lot of good reports from our customers saying that they've been a useful tool. People actually hold little lunch and learns in their office showcasing the webinars because they've been a good tool for people to kind of get caught up on how to use the Celigo, as well as learn how to use new applications on the system. So, and if you guys like the content, let us know. If you want us to cover new content, let us know. I'm always looking for new topics. And Amy, don't we have another webinar type? It's informational based more than application based?
Yes, that's right. We also have informational webinars. They're meant for people who have not already purchased a Celigo or purchased one of our instruments. Those are kind of more for people who are just kind of getting started. They're interested in the instrument, but they're just not sure exactly what it can do yet. They're looking into purchasing it just to see how it works. And those just kind of give more of like high-level information on just how our different instruments might work with different applications for you. And then we have like the ones like today that are user training. So once you've already purchased the instrument and you really want to dive deeper into certain applications and things like that on how to specifically use it and what buttons to use and things like that. So we do have informational webinars every month. You can also find our registration forms for that on our website if you'd like to. We have them on different topics every month and for our different Celometer or Celigo instruments on different topics. So feel free to check those out on our website at nexcelom.com. And you can also find all of our past webinars on nexcelom.com as well under the support and help and training page. We have all of our past webinars up there for you guys to watch those as well. And like Sarah said, it's a great resource and a great reference for anyone using our instruments. So yeah, we always have a wealth of information for you guys. But unfortunately, I'm not seeing any questions coming through. So I guess that will conclude the webinar for today. If you guys do think of any questions for us later on, feel free to email us at support@nexcelom.com, or you can type them into the survey at the end of this webinar. We'd be happy to review any questions or topic suggestions that you guys have. I appreciate everyone joining us today, all of our attendees. And Sarah, I think that was a wonderful presentation. And I hope everyone has a really great day.
Thanks, everyone. Thanks, Amy.
Goodbye.